is Alex, and you can find me on my Twitter and on my website if you wish. Today I'm going to talk to you of a tale of two Monix streams. But first, let's talk about what is Monix. So it's a Scala library for composing asynchronous programs exposing multiple primitives like observable, task, coeval, iterant, and many low-level concurrency primitives that belong in a standard library. It's been a type-level project, which for you it means that it adheres to certain quality standards. And I just released 3.0 milestone 1 before coming here. Yeah. So what's coming in 3.0 is deep integration with type-level cats and its type classes, a new iterant data type for lawful pool-based streaming, and major improvements to observable, task, coeval, and cancelable future. Yeah, we've got a future in there. So the project started sometimes in 2014, and it was named Monifu. I started it at 2 o'clock at night. It was developed at Eloquentix mostly for monitoring and controlling power plants. We used it for that, and thus we continued development on it. It was originally inspired by RxJava and REACTIVE-X, and renamed to Monix on December 30th, 1 year later. So strange things happened to me around New Year's Eve. And in case you were wondering how that logo got made, I made it in Inkscape. It's Scala plus love, blue love. Let's talk about observable. So observable is about push-based streaming. Its origins are in Netix.net, also known as reactive extensions, also known as REACTIVE-X, exposing the observable pattern built at Microsoft by these people, out of which Eric Major has provided the inspiration for me in his reactive programming course on Coursera. The basic idea being that starting from the iterator and iterable interfaces that we all know and love, this describing a pool-based streaming approach, a dirty one, but it's really effective at iterating over streams, over arrays and various data structures. We can then describe these as functions, side-effectful functions, using standard Scala types. And if we reverse those arrows, we get a push-based stream. This being the observable and observer. So, and because we are OOP developers, we are going to explode that in OOP interfaces. Also adding a cancelable action that can be triggered to cut the connection between the producer and the consumer. Now, of course, there are problems with this these interfaces. This describes a little the grammar of the producer, so it keeps pushing on next events until on error or on complete happens as final events, after which nothing, or we can cancel it, but this is something that's concurrent with the producer's run loop. And Eric Major is fond of saying that observable is the dual of iterable, and when speaking of duality, you can think of that as being its evil twin. So the problems of the protocol as described in Netix.net is that it's a pure push-based protocol, and thus it provides no protections against slow consumers. So we have to work with unbounded buffers and throttling. And sometimes that works fine, but not always. And as a matter of trivia, their flat map implementation is aliased to merge map because their concat map, which is the monadic lawful bind, is unsafe due to the implementation requiring unbounded buffers. So there's inherent unsafety in using it. And then the lightband people, in collaboration with one RX Java author and the authors of the Disruptor project and others, I can't remember right now, have come up with these interfaces describing a protocol for producer-consumer communication that introduces back pressure. So you receive a subscription that has a request on it with which the consumer says, I want the next 10 elements, and this creates a batched back pressure model, let's say. So around that time, but a little before that actually, I had the idea, and it's really not an original idea because it's obvious, to use futures, Scala's standard future for back pressure, because that's what future was built for. And simply have the producer back pressure on the on-complete event of that returned future from on next. So the producer pushes an event, the consumer returns a future, the producer has to wait on that future, and so on and so forth. And the second idea I had was to introduce an acknowledgement as being an enumeration that can be a continue or a stop, with which we can signal the intention, either continue with the next element or stop. And the cool thing about this enumeration is that it inherits from a future of acknowledgement being a sort of a recursive type. And so we can use that in an optimization, because when we say that onNext has to return future of acknowledgement in this interface, in an observer implementation, we can simply return continue or stop as an optimization, this being an implementation of an observer that simply sums up numbers. It's dirty, but it does its job, and it's really efficient. So we can collapse synchronous pipelines, basically, until an actual asynchronous boundary happens. Talks of using future have been in RX Java as well, but they didn't want to go that route because they said that it is slow, but with a little creativity, it's not slow, and I think it is higher level than using those interfaces defined in reactivestreams.org, which are meant to be middleware anyway. But the important thing to take away from this is that observable is a high level data type, and we already have a fold operation on it with which we can sum up numbers along with dozens of other operators. And observable also suspends side effects. Nothing actually executes until you call subscribe on it, this being an important point. Subscribe into which you give an unsafe observer that processes the incoming elements, but you don't have to use subscribe. Subscribe itself being a low-level operation, you can simply convert an observable to task usually. And you've got fold methods, for example, that are suffixed with L in the API that simply give you a task, which you can then combine with other tasks and so on and so forth. So you can build a composition of observables and tasks in your program without ever having to call subscribe or run async until the end of the program, so to speak, because we are functional developers in addition to being OOP ones. So you also have consumer, which is basically a function that converts observables into tasks, you can also describe a fold with consumers. By means of consumer that also sums up numbers, a really important operation in general. And what would we be without claiming that observable isn't a monadic type? It is. It implements a very safe flat map that does back pressure. It's not alias to merge map, so this is the concat map. It's lawful, it's back pressured, and it has versions like map task or map eval coming from the deep integration that we now have with type level cats. So map eval works with the new effect type class, and you can shove the new I/O data type in it, for example. So you can map over I/O values or over task values, or actually also future values. You also have map future. The API is not minimal. I don't really believe in minimal APIs. So, as I was saying, observable suspends side effects, and this is the recommended way of working with it. In this example, we are reading from a text file and then emitting those lines that we've just read. The really cool thing about it, if you're an FP developer that has played with alternatives like, for example, FS2, which is a totally awesome project, is that observable does not need an I/O task for evaluation because observable itself is an I/O-like data type. So it can suspend side effects all by itself, it implements its own run loop and so on. But it can integrate with those, and the things that observable is really awesome at is at doing reactive stuff like merging an unlimited number of observables, or switch map, which is an operation that cancels the previous child observable when a new element gets emitted. And in terms of switch map, you can implement any throttling operator, but you don't necessarily have to implement throttling operators because observable already has those. So you can sample, debounce, or echo the last element emitted, or you can repeat the last element emitted whenever the source goes silent. And it's really awesome to work with this when you're working with time series data, like when, for example, when you're pushing into OpenTSDB having poor performance because of HBase in general, so I had to do something like this at some point, sampling the distinct elements of the source by 1 second, but we still want to persist repeated events, even if those events are the same, to have some history in OpenTSDB, but we want to sample those at a smaller rate. So we say that in case events are repeated, then we sample those every 5 seconds instead of 1 second. So for such use cases, observable is awesome. This is another example, the publish selector that gives you a function which injects a hot data source in there. The hot data source is something to which you can subscribe multiple times and receive the same events, and we can operate on this example shows you a split in two, so it splits the stream in two, it operates on both splits and then remerges them. So this is an example of a split followed by a join, basically, and it's perfectly safe and back pressured. And another thing that observable does really well is buffering, because sometimes you can't control the source of the data. For example, in user interface, you can't back pressure the user to not move the mouse or to press the keyboard. So sometimes you end up needing to do buffering, and in case the buffer is limited and you want limited buffers, you can implement an overflow strategy like drop incoming events and then trigger a warning once the consumer recovers. So you can also warn either the user, or you can log that in a log file that events were overflowed, that an overflow event happened. Or for performance reasons, you might want to introduce an asynchronous boundary in there that's buffered and that back pressures the source after the buffer is exceeded. So many optimizations have gone into observable in general, and to give you a sample what we did for FlatMap, because of the details of the protocol, we've got some concurrency in there. The details are a little ugly. Basically, when we send the final on-complete event for optimization purposes, and because it's a good idea for communications protocol in general, we are not back pressuring on the last on next event. So on-complete can be sent without back pressuring on the future of the last on next event. And because of that, we've got concurrency in the implementation. And because we have concurrency, we had to optimize it. And what we do is to model a complex state machine for eliminating those synchronous boundaries. notice that is kept in an atomic reference, which is then cache line padded for avoiding false sharing, an effect that happens when multiple threads hit the same volatile variable. And it uses get and set platform intrinsics available starting with Java 8, which, for those in the know, is something that's hard to do because you have to reason a lot about ordering, and you need to ensure that your logic runs on more processors than Intel. Intel CPUs are in general well behaved, so and you need to ensure that whatever you wrote is within the constraints of the Java memory model such that it runs on ARM. Well, I've got Android users and they haven't complained until now, so I'm guessing it's fine, but in general it's really tricky to do this. So in case you, all the dirty stuff goes into the Monix execution subproject, and there I've got atomic references that do cache line padding in case you want them, plus utilities for modeling those compare and set loops based on macros to not lose efficiency there. So you've got cool stuff in Monix execution, check that out. And another thing that I've been doing is to integrate JC tools for non-blocking queues. This is an awesome project that's used mainly by library authors, modeling non-blocking queues for various scenarios, our scenarios being mostly multi-producer, single consumer scenarios, such that the consumer does not contend with the producers, this also being important for performance. And as a consequence, observable usually has best-in-class performance, meaning that synchronous ops have near zero overhead. It can be more efficient than Scala's iterable for synchronous operations, and even in operators that have concurrency in them, like flat map, we can usually optimize those synchronous pipelines. And we achieve referential transparency, meaning that the API is pure, but the internals can get really dirty, but it's totally encapsulated. So pure API, dirty internals, it's what I like to do. Yeah, so the alternative, because I don't believe in silver bullets, I'm now providing in version 3.0 a pool-based streaming approach as an alternative to the classic iterable that is a purely functional solution, as you'll see. And right now we are going to go into a little exercise of FP design, because I like to show you how things are implemented, and I like to see that from others. Goethe once said that architecture is frozen music, which made John Bentley say that data structures are frozen algorithms. You might know John Bentley as the author of Programming Pearls. And this is one of the key insights that I learned and that I'm passing on. In general, to design FP-ish things, you need to freeze algorithms into a data structure, this would being the easy way to do it. You need to think state machines most of the time and transform a strict value into lazy functions. Well, I mean, Scala is a strict language. In order to achieve laziness, the logical thing to do is to introduce functions. And we can start from a simple state machine, because we think state machines, and we can start from linked lists. The linked list from Scala is a simple state machine. At every step, we either get a tuple of the current element plus the rest of the stream, the tail, or we get the empty stream, which usually signals the end. This being Scala, this list is strict, but we need laziness, so we transform that into something that uses functions, or parameterless functions, also called thunks. So this would satisfy our requirement, even though it's not ideal. We'll see that in a moment. And we are also going to introduce a hold state that can also signal an error, because we hate throwing exceptions. Right? So the hold state represents the empty stream with an optional error. For resource management, this being in general a weakness of iterable-like data types, or of list t from Haskell, we introduce another function in there on each state called stop that is meant for doing early stop, for early releasing of resources. So if you think about it, the consumer at each step of the way, it has a choice to make. It can either go for the rest of the stream, continuing with processing, or it can do an early stop to stop the execution of the and release whatever file handles and sockets it has allocated in there. We also need a suspend state for suspending side effects and for eliminating elements from the stream in case we need. And right now, next, suspend, and hold are the three states we need to start describing operations on this new data type. We can describe, for example, a filter operation, and like all good FP developers, we start pattern matching on our algebraic data type. Filtering an empty stream, of course, does nothing, so we simply return that. In case we are dealing with a suspend, we build a new suspend state that simply captures a new function that applies the filter to the rest of the stream. So it's a recursive call, but the recursive call gets suspended inside a closure, and we do the same for the next state, where we execute the predicate, and if true, then we return next, or otherwise return another suspend. Also with a recursive call being suspended with filter being applied to the rest of the stream. But that is not sufficient in Scala, because Scala doesn't do tail call eliminations. So what we need here are data types that with which we can describe such recursive calls without having the stack blown up. So can we use future? Well, we could, but it would be totally useless because future is a strict value wannabe. So future is not a function, and for example, that stop reference there would be totally useless because future is not a function again. But as I've said, to turn in Scala things in lazy values, we can simply turn them into thunks. So we could work with thunks returning futures, and we could alias that to task, but we already have a task defined in Monix. We already have a task that's very performant in Monix, so we could use that and this would work. And the cool thing about it is that it would be able to describe asynchronous computations as well, task being a function. We could work with coeval, which is like a task that is not capable of asynchronous computations, but is still capable of laziness and suspending side effects. We could work with a new cats effect, IO, data type from cats, or with the upcoming Scala Z8 data type, whatever. Or with CANCELATION, although here, as you'll see, we would need in the implementation error handling, and CANCELATION does not implement monad error being a co-monad. But we could go the way of parametric polymorphism and abstract away the F data type that is being used. We could say we want to work in this data structure with any F data type and then apply the restrictions on the operations themselves. This is called higher order polymorphism. I hope it is. Anyway. So filter now, in case we would be describing it, building the rest of the stream with a filter being recursively applied to the rest would involve a call to the map function. So we would say rest map filter. Because our F data type must implement the new sync type class from cats effect, sync being a type class that is a monad error, so that has a memory safe flat map implementation, and that can suspend side effects. So any sync data type here would do, including the task from Monix, including the new IO data type from cats, including coeval, not CANCELATION. As I was saying, CANCELATION is a comonad and it's a little incompatible with monad error. But we could use, we could do something with either T, let's say, and deval. So this is also a method of polymorphism called bringing your own boost to the party. So in order to work with this, you instantiate the new iterant with task. So you say iterant of task, or iterant of IO, or iterant of coeval, and you would work with it. And the really cool thing about it is that the F data type that you plug in there completely changes the nature of your stream. Coeval is not capable of asynchronous computation, but it gives you a guarantee that the result is available right now. So it's a totally different stream than one that would be powered by task or by IO. So I think it's pretty cool, and even though I'm usually wary of introducing too many abstractions because it increases the barrier to entry, I think in this case it is worth it. In this case, not in others. But when doing stuff like this, the issue is that we've got performance issues. What we just described is a linked list, a lazy one, but it's a linked list regardless, and the problem is that linked lists are terrible in terms of performance, and functional programming uses linked lists everywhere, and so we've got a problem, especially in Scala, which is not optimized for laziness, because asynchronous or lazy boundaries are also terrible. So what we need to do there is to find ways to work with arrays and to avoid lazy asynchronous boundaries as much as we can, especially in Scala with its strict evaluation. So I wonder what can iterate over arrays efficiently just as well as over other data structures. I mean, if we had such a abstraction, I mean, now we know what iterable is good about. I mean, except for boxing, which can have significant overhead, except for that, iterable and iterator have zero overhead when going over arrays, and also the really cool thing about that is that they provide efficient head-tail decomposition, meaning that you can take the current element and pass the rest to somebody else. This is in comparison with a push-based protocol like what Observable is doing. So we can simply shove those iterables and iterators into new states because we have a state machine that we can control, and do stuff in batches when we can, right? So what we did here was to transform a purely functional data structure into a not quite purely functional data structures, because iterator is side effectful, right? But you have to consider a couple of things here. Iterators and iterables are so common in Scala that you are going to wrap them anyway, so you could introduce special cases just for optimizing that, because you're going to wrap these all the time. And also, we are capable of suspending side effects, so all operators on iterant are going to be referentially transparent, and it's really worth it for performance reasons, as you'll see, because right now we are going to do a comparison between observable and iterant. And as a case study, I implemented scanEval, and it's in that pull request. If you want to take a look at it after the presentation, it's a really beautiful pull request because it has implementations of scanEval for both. Scan is basically like a fold left that admits intermediate states at each step, and scanEval can flatten IOs and tasks and whatever F data type that you're using. So for iterant, the signature looks like this. So it's basically a fold left that emits intermediate states, and you also have scan on Scala standard libraries. And here we are requiring F to be a sync type class, which again is a monad error that has a memory safe flat map and can suspend side effects. And implementing it for iterant, it's not not easy, but reasonable, let's say. I mean, you describe a loop and you don't have to understand the implementation. I'm just showing it here for you to know what we're talking about. So you do pattern matching on the states and then you return something. Pattern match, return something, and we build that state incrementally. It's standard functional programming. You have some gotchas related to recursion, but it's doable. On the other hand, on observable, we require an effect being data types that have an unsafe perform IO on them, so we have less flexibility here. And also the implementation has to pass through task, because observable does not have a pluggable F type. So we transform those data types into task, and then we compute that, and then on task we do something like on complete do that. So yeah, and the implementation for observable, I can't fit that on one slide because it's basically just like flat map, and with the aforementioned implementation, with all the concurrency problems that it has and the optimizations, but when doing a benchmark, observable is much better than iterant. So the blue bar is observable flat scan that works just with observables. The orange bar is observable scanEval that works with task, and the gray bar is iterant scanEval that works with task again. So it can have 3 times the throughput if used right. With one exception, if you introduce an asynchronous boundary at each step of that scan, you get better performance for iterant. This one is interesting because you basically have some overhead into pulling values out of those asynchronous values, which are actually futures. So so we can conclude from this that observable has performance and iterant has reason. I'm not kidding. But in another case, when we are talking about synchronous operations, and in this case we are measuring the performance of a map followed by a fault, so there's nothing asynchronous about that. The observable performance can be 10 times better than an iterant described with the next stage, so simple iterants that introduce those tasks at each step of the way. So this is precisely the reason why we're introducing batching, right, by means of iterable and iterator, because it can bring up performance quite a lot in case we need that. So another cool difference between them is that observable cannot express fault right. Fault right is a really cool operation, but it reflects the shape of the data structure, and we cannot express fault right for observable because it does not afford an efficient head-tail decomposition. And whenever you subscribe to an observable and you make it tick, you can only have one subscriber to that observable, and you cannot switch subscriptions and so forth. So we are forced to work with substitutes. Like, for example, I introduced fault while left, where you return a neither, and it keeps on going until a right value is returned, after which the process is short-circuited. So this can solve some use cases that a fault right would solve. But I've said iterable there. On iterant, we can describe a fault right that is slightly different than the fault right on list, because again, the fault right reflects the shape of the data structure, and we've got a stop action that's being pushed there. So in my opinion, it's a little unsafe to use because the user has to be aware of when the process is being short-circuited and when it is stopped. This would be exist, and basically we keep on going until the predicate is satisfied, and then we return stop followed by the result. And this would be for all, where we return stop followed by false whenever the predicate is not satisfied, and then we can do concatenation. And again, in case of concatenation, we simply have to transport stop along in the states that we are building. But it's doable, so it just has a slightly different signature. Because, you know, this was an embarrassing Twitter moment for me. I was complaining. I complain a lot. You should follow me. So I was complaining about fault right, not as I wasn't able to describe it for observable. And I then later had a realization that I should have had by reading papers, but I've had it by banging myself against the desk. So I finally understood that fault left reflects the shape of the data constructor for lists. And so that's why I wasn't able to implement it for observables, and why it needs a slightly different signature for iterant. But all is well. So, as conclusions, observable is best for reactive operations, shared data sources, throttling, buffering, and performance. I really mean it. When comparing it with purely functional abstractions, observable is top-notch, and iterant is best for easier implementation reasoning and quickly converting task I/O calls into streams. It was built for that. And both implement the reactive streams interfaces, so you can convert them. Actually, at this point, you can only convert an iterant to a publisher and not a publisher to an iterant, because that means turning the model on its head. But when the file 3.0 hits, then you'll also have it both ways. And both do back pressure and safe error handling, and can express asynchronous streaming. So, in closing, I've heard this idea that Scala can be slower than Haskell when doing FP, and there's some truth to that, because Haskell is optimized for non-strict evaluation and for usage of I/O. And in Scala, when you're doing programming like in Haskell, well, of course, it's going to be slower. But if you embrace a hybrid approach where the API is pure, but the internals are dirty, well, good things can happen from that. So, yeah. You can follow me. I rant a lot, so any questions? I don't know if we have time. Yeah.
Yes. So, how much is the new iterant intersecting with FS2's futures? Like, is it like somehow the same, or because FS2 was also pull-based, I think?
I've been told that iterant does what FS2 did 4 years ago. I'm not sure about that. I think it is different, but yes, there's overlap. Yeah. No more questions?
How do you test other things?
Right, so there are shared testing. So, yeah. First of all, we use Scala check for property testing. We have a lot of tests. We simulate asynchronous execution for deterministic tests. I mean, there is like a test scheduler in there that randomizes the runnables being registered and so on, and it simulates basically synchronous execution. And the tests are shared between the JVM and JS, and because everything is compatible with Scala JS. And then where tricky areas of concurrency need to be tested, there are also JVM-specific tests. So, and the test coverage is pretty good. But in general, Scala testing, Scala check, faking asynchronous execution, and so on. And plus, I also integrated. I mean, when speaking of type class laws, I also integrated CATS laws. So we have proof that everything is a monad and so on. So Yeah.
You talk about throttling and these kind of things, but is there other primitives to limit the execution context to parallelism or things like that?
Can you repeat the question?
Is there some primitives, higher level primitives to limit the parallelism or control the parallelism of the execution?
Yeah, we've got that. First of all, on observable, we've got map async that can do stuff in parallel, but with a limit. There's also a semaphore implementation for task and for future in Monix execution that can execute stuff, but with a limit. Like you can say, I want at most 10 tasks to execute at the same time. So yeah, it provides, there are a couple of ways to do it, and there is an article on how to achieve parallelism on the project's website in the documentation. You should check that out. Okay, I guess this is it. Yeah.